Hello friends, in this session we are going to talk about the different conditions which are required in order to have a continuous torque. Let's begin. Yes, conditions for having continuous torque. Yes, so now first of all we will try to understand what is the importance of a continuous torque. For example, let us take generator. Now, in the case of generator, we know that prime mover is the input. Basically, we are going to rotate the prime mover. For example, this is the prime mover. We are going to rotate the prime mover like this. Right. Now, what is going to happen? There has to be some opposition in order to deliver mechanical power from the prime mover to the generator, which will be absorbed by it, and it will in turn deliver electrical power. Now, see here, just imagine. This is the prime mover. I am rotating the prime mover, right? Now see here. For example, if this is my generator, right? Prime mover is moving like this. Generator is opposing the movement of my prime mover. Now, beyond this opposition, I am going to apply torque. Beyond this opposition, I am going to apply torque, in which so that mechanical power will be delivered by the prime mover. Now just imagine if this opposition from the generator, basically opposition from the generator means what? Generator torque, right? See here, this is prime mover rotating in this direction. Now what is happening? My generator is trying to stop this like this, right? This is my generator, it is going to stop like this. Now beyond this opposition, I will have to rotate my prime mover, so that mechanical power will be delivered, which will be absorbed by the generator. In turn, I will get what? Electrical power at the output. Now, just imagine this particular torque from the generator. If it is there for some time and after some time it is not there, means that, see, at starting generator torque. Now I am moving my prime mover beyond that opposition of the generator torque like this. Torque is gone. Again torque came. Again torque went. Again torque came. Again I am rotating. Again torque came. Which means what will happen? The moment the opposition from the generator is not continuous, I am repeating, the moment the opposition from the generator is not continuous, the prime mover will not be able to deliver mechanical power continuously. Which means my generator will not be able to absorb that power continuously, which means my generator will not be able to give electrical power continuously. It will not be able to give the electrical power continuously, which means the opposition from the generator, or we can say the generator torque, has to be continuous, so that continuously mechanical power will be absorbed by the generator, and at the output I will have continuous electrical power, right? So the importance of having a continuous torque is this. Now see here. Now see here, this is bullseye indicating it is a stator. Let us say that I have a stator like this, right? This is north pole, this is south pole, right? We know that flux lines will be like this, right? Now see here, inside this I have a rotor like this. Now what I am assuming, that this rotor has its own flux, which means there must be some or the other conductors here like this, and there must be some current flowing like this, any current, right? And because of this I am going to have some flux. Now see here, this is into the board, out of the board. I will be having flux in this direction, am I right? Which means from this particular portion of the rotor, flux is outwards, which means this is going to become north pole, and this is going to become south pole. South pole only, right? Because this flux will go here, come back from this one, which means from this one it is going to be, from here it is going to be incoming to the rotor piece, which is the reason it is going to be south pole. Now see here. Yes, now see here, what will happen? This north will get attracted to this south, and this south will get attracted to this north, which means torque is going to be in this direction. I am not saying that the direction of rotation is in that direction. I am not at all saying that. I am only saying that the direction of torque will be like this, which means in this case torque is produced. Am I right? In this case torque is produced. Now see here, another case. Let us consider the same stator. It is the same stator, north pole, south pole, south pole. Now see here, if I have a rotor like this. Now, for example, here if you see stator poles were 2, at the same time 2 rotor poles were there. Here if I see there are 2 stator poles. For example, if I have 4 rotor poles like this, let us see. These are 4 rotor poles. By the way, this is a rotor, so there has to be a shaft key, right? See here, this is the shaft key of the rotor. Now, for instance, I have north here, south here, north here, south here, right? NS is there. Now see, what is going to happen there, we will understand. See here. If you observe, this south of the rotor will get attracted to this north of the stator. Perfect. This north will get repelled by this north, right? This south will get repelled by this south. This particular north of the rotor will get repelled by the stator north. And here if you see, what is going to happen? South of the rotor will get attracted to the north of the stator. Whereas here if you see, what is going to happen? This is going to get attracted. South of the stator will get attracted to the north of the rotor. Now see, what is happening? This portion of the rotor is trying to move upward. Torque in this particular portion is upward. This particular portion it is downwards. This particular portion torque is upwards. This particular portion torque is downwards. Which means here if you see, net torque is 0. Net torque is 0. And here if you see similarly, what is happening? Net torque is 0. Right, because see here, north is repelling, south is also repelling. This is trying to move it this way, this is trying to move it that way, which means net torque is 0. Right. So see here, now you will say, sir, it's okay, we have understood about it that in this particular case electromagnetic torque produced will be 0, but why are we only considering north south? Why are we not considering all as north, all as south? Means, why are we not considering all the poles as north, or south? The reason is, see here, this particular machine which is shown, this red which is there, this is called as heteropolar machine. What is it called? Heteropolar. See here, heteropolar. And if all the rotors are north, or south, then that particular motor is called as, or that particular machine is called as homopolar machine. Now, student ask me, sir, heteropolar machine only, why are we not considering homopolar machine? Yes, there is a reason why we are not having homopolar machine in practice or in existence. There are some reasons, some economical, electrical reasons as well. We will talk about them when time comes. Right now, just remember one thing, that in the whole syllabus, in the whole existence, there will be only heteropolar machine. There will never be homopolar machine, that is for sure. Why it is there? Time will come. I will explain you why we are not having homopolar machines, why they cannot be physically existing. Right? Now, point is very simple. We will always going to have heteropolar machines in practice. In existence, only heteropolar machine will be there. Rest, no machine will be there. Homopolar machine cancel. We will talk about it later when time comes. Now see here. Observe these two diagrams. Yeah. See here. What is happening? See. In this particular case, there were two stator poles and there were two rotor poles as well. Whereas in this particular case, if you see, two stator poles are there, but at the same time there are four rotor poles. And we have also seen that when number of stator poles is equal to number of rotor poles, means in this particular case two stator poles, two rotor poles, in that case electromagnetic torque is going to be developed, right? Whereas if you see here, what is happening? The moment the number of stator poles and rotor poles is changed, torque is zero. See here, two stator poles are there and there are four rotor poles. See here, four rotor poles, which means in such a case torque will be zero, which means, see here, condition number one. What is that? In order to have a continuous torque, first and foremost condition is, see, number of stator poles should be equal to number of rotor poles. What have we done? Number of stator poles should be equal to number of rotor poles. See here, stator poles are 2, rotor poles are also 2, torque is produced. Here if you see, stator poles are 2, rotor poles are 4, which means they are not equal. That is the reason torque is 0. This is the first condition. Now, is this the only condition which is to be satisfied? Let us see. Yeah, see here. For example, this is a motor. For example, this is a motor, right? Now, north-south of stator, north-south of rotor. Torque is produced in anti-clockwise direction, already proved, no problem. Now, I am holding the rotor here like this. See here, I am holding the rotor like this. I am holding the rotor like this. At that time, what is going to happen? It will give me some twisting moment like this in this upward direction. Why? Because there is already some torque. The machine is already producing a torque in anti-clockwise direction. So even if I am holding it, it is going to give me a twisting moment like this. So now I am releasing it. Now I am releasing my hand. What will happen when I am releasing it? This south will go here. This south will go here and this north will come here. This south will go here, this particular north will come here. Now what will happen, sir? Will there be any torque further? Think. Will there be any torque further after having a 90-degree rotation in this particular fashion? Will there be any torque further? Let us see. This north and this south attracted, north and south attracted, right? Which means now they are in alignment. The stator poles and rotor poles are aligned, also called as magnetic locking. See here, in this particular case, what is happening? North is getting attracted to south, south is getting attracted to north. That is the reason what is happening. Rotor poles and stator poles are now aligned in one direction, which means there will be no further torque. There will be no further torque. Now see, the moment there is no further torque, which means there has to be some other condition also which has to be satisfied. What is that condition? Let us discuss now. Yes, see here. Stator, north pole and south pole. Now, in case of rotor, let us have a circular rotor right now. Let us see. Now, on this rotor, let me have two conductors like this. And let us assume that here cross current is flowing and here dot current is flowing, so that we will have a torque. We will see how. The moment here is cross, here is going to be dot, which means, now wait, first of all, this is a shaft key. Remember that. See here, this is the cross, this is a dot, which means right hand thumb rule, I am going to flux in this direction. Flux will be in this direction. What will happen? Flux is like this. The moment flux is like this, if you observe this particular part of the rotor, what is happening here? Flux is going to come out of the rotor here. In this part, flux is going to come out of the rotor, which means this part becomes north pole of the rotor. If you see here, what is going to happen? Flux is incoming to the rotor. In this particular portion, what is happening? Flux is incoming to the rotor, which means this is going to become south pole here, like this. Agreed? No problem till then. Now see, very important. Yeah. This is north pole, this is south pole. If you observe here, what is happening? See, this north and this north will repel each other. This north and this south will get attracted, which means this is going to come here. Torque will be produced in this direction. If here, if you see, south will get attracted towards north, going to get like this. Agreed or not? Of course agreed, right? Now, which means that torque will be in this direction. Electromagnetic torque is in this direction, right? Rotor is like this. Now next, see here. For example, it is a motor. I am holding the rotor of the motor like this. I am holding the rotor of the machine like this. Now see what is happening. In this particular case, when south is here, north is here, right? Torque is in this direction. Now, what will happen? I am trying to hold the rotor like this. Holding the rotor like this. What will happen? I will have some twisting moment like this. I will have some twisting moment like this. Now I am releasing the rotor, which means this is going to move like this, which means this north will come here and this south will come here. This north will now come here and this south will now go up. Now here, if you see, what is going to happen? There is going to be flux alignment. Basically, if you see, stator poles and my rotor poles are going to get aligned, which means there will not be any further torque, already studied. Now, in the initial case here, when here is north, here is south. Yeah, see here, when if you see, here is north, here is south. What about the direction of MMF? Now let us discuss a bit about MMF. See here. What is MMF? MMF is nothing but number of turns into current. Now, what is flux phi? Flux is nothing but MMF upon reluctance. Right? Now see, observe very carefully. If I am keeping number of turns as constant, what is going to happen? See here, if I am keeping number of turns as constant, which means MMF is proportional to the current, right? And if you see here, if here I am considering reluctance is constant, so now in this case, what is going to happen? Flux will be directly proportional to the MMF. Am I right or wrong? Flux is going to be directly proportional to MMF, which means, now you tell me here, in case of rotor, first case, initial case, when this was north pole, this was south pole, flux was in this direction. Now you tell me, from this relation we have got that flux and MMF will be directly proportional to each other, which means the direction in which flux is set up, in the same direction MMF will be set up, which means if flux is in this direction, MMF will be in this direction only. So let us say that this is rotor MMF FR. Now let us talk about stator MMF. if you see here, the stator MMF here will be from north to south only. Why? Because flux is from north to south. That is the reason MMF will be also be from north to south. So this is north, this is going to be MMF. So this is going to be F stator, stator MMF. By the way, what is MMF? Magnetomotive force. I hope you all know that, right? Magnetomotive force. Already we know that from the basics, right? Now see here, this is the stator MMF, this is going to be your rotor MMF. Let me draw it here. See dear, I am trying to represent the same here. Stator MMF is in this direction, up to down, like this. F stator. And if you see rotor MMF is in that direction, which means rotor MMF is in this direction, FR. Now, closely observe, see here, what is going to happen? Now, we know that torque was produced, initially torque was produced when this rotor MMF was in this direction and stator MMF was in this direction. Right? Torque was produced when rotor MMF was in that direction, stator MMF was in this direction. Now, when torque was not produced, let us see. For this particular position of the rotor, means I was holding the rotor like this, torque was there in clockwise direction, then I was holding the rotor here, right? Then I release the rotor. What happened? South, which was here, it actually went here, north came down. That is the reason, if you observe what happened here, let us see. This was north, which means flux is going to come out of the rotor here, right, and into the rotor here. Am I right? We all know that. See, inside a particular bar magnet, flux lines flow from south to north, and out of the magnet it is from north to south. Similar thing is happening. If you want to verify the same thing was happening here also. Flux was moving from south to north, inside the rotor. Here also, see here, flux will be moving from south to north like this, which means, let us say that the MMF for the second condition is in this direction. Let us call it FR2. Now, see here, closely observe. This particular MMF is for the second condition. Second condition is which? When north pole has traveled here, south pole has traveled here, because of which MMF, right? It was in this direction. Agreed? Right. Now we know that in the second condition, what happened? In the second condition, there was no torque. In the second condition, torque was 0, and if we talk about the first condition, here torque was there. What does this mean? What is the observation from here? What is the observation? See here, in the second case, in case of FR2, torque was 0 because south was here, north was here, rotor poles and stator poles were aligned, which means further torque is 0. That is the reason in second case torque is 0, shown by green. In the first case, what happened is, see here, in the first case, when my rotor MMF was in that particular direction and my stator MMF was in this direction, which means there was some displacement between them. When there was some displacement between there, what happened? Torque was produced. Now, let us conclude this. Now, see here, chill, take a deep breath. See, in the first case, what happened? First case, the MMF was in this direction. In the second case, MMF of rotor was in this direction, which means see here, in the first case, MMF for the rotor was in this direction. In the second case, MMF for the rotor was in this direction. It is the same rotor, right? Rotor rotated in 90 degrees. It came here. No problem. We understood that. See, second case, torque was 0. Why? Because stator and rotor poles were aligned. In the first case, stator and rotor poles were not aligned, and that is the reason there was a torque. What does this mean? This means that stator MMF and rotor MMF has to be stationary with respect to each other. My rotor MMF should not move with the rotation of my rotor. The moment rotor MMF is actually moved from FR1 to FR2 like this. See here. The moment my rotor is rotating like this SR came here, NR came here, right? Because of which the direction of my MMF also changed from FR to FR2, from FR to FR2. Now, what do we understand here? This means that the stator MMF and rotor MMF has to be stationary with respect to each other, and they should be displaced. See here, concentrate. Here if you see what has happened, stator MMF and my rotor MMF are stationary with respect to each other, right? Here also if you see with respect to each other, both are stationary, but there is no difference between their angles. There is no difference in their angle. They are in phase. They are in the same direction. There is no angle difference. Now see here. For this case, when we are talking about the first case, there was some angle here. 90 degrees, for example, here. Right? Which means, what do we understand from here? In order to have a continuous torque, stator MMF and my rotor MMF has to be stationary with respect to each other, which means they should not be rotating. Even if my rotor is rotating, my rotor MMF should not rotate. They should be stationary with respect to each other, and at the same time there should be some displacement angle, because we have seen when the displacement angle is 0, here if you see torque is 0. Second case, green case, second case, torque is 0. Let me write down. Yes, so now we have got the second condition. What is that? What is the second condition? See, stator MMF and rotor MMF has to be stationary with respect to each other, and there should be some displacement between them. Means stator MMF and stationary with respect to each other. And displaced by 90 degrees. Is that clear? Now student will ask me, sir, should the stator MMF and my rotor MMF should be displaced by 90 degrees only? Is it correct? Let us find out. See. Yes. If you see here, here the angle was 90 degrees. Agreed. But will there be torque if there is other angles than 90 degrees? Means except 90 degrees. Apart from 90 degrees, will there be torque for other angles? Let us check it out. See. Let me have a stator like this. See, let me have a stator like this, NS, and at the same time let me have a rotor like this, which is having North pole here, south pole here. Now, what about stator MMF? What about stator MMF? Stator MMF is like this, F stator, north to south, right? What about rotor MMF? What about rotor MMF? Flux will be coming out of this, which means if flux is coming in this way, MMF should be in this way. Now, you please tell me, is this angle 90 degrees? My observation only, is this angle 90 degrees? Not 90 degrees, but let us see if there can be torque. Let us check that. This south will get attracted towards this north. This north will get attracted towards this south. South is getting attracted to north. North is getting attracted to south, which means torque is in this direction. Torque is in this direction. Which means, see here, concentrate, which means even if the angle is not 90 degrees, even if the angle is not 90 degrees, there is going to still be torque. There is going to be a torque. And we already know that if, for example, it is a motor, I am holding it like this. Torque is in this direction, which means I will have a twisting moment like this. Now I am releasing my hand. The moment I release it, this N will become here, N will come here, and this south will go up like this. This rotor will get shifted like this. Now here if you see, angle is going to be 0. Let us say that if it is FR2. If you see here, angle between the stator MMF and my rotor MMF is 0 here. In this case, will there be torque? No torque, because it is aligned, magnetically locked. Moral of the story. Yes, so from the example we understood that it is not necessary that it should be displaced by 90 degrees. It is not at all necessary. Rather, it should be non-zero angle. Any non-zero angle will do. Only thing is, angle should not be 0. Angle has to be non-zero. Any angle will do. 1 degree, 2 degree, 5 degree, 10 degree, 180 degree, any angle will do. Just it should not be 0. Right? Please note this down. This is very important. These are the two conditions which are to be satisfied in order to have a continuous torque. Now, let us talk a bit about commutator. What is a commutator and all? Let us see. See here, let me have a north pole. Let me have a south pole like this. Let me have a rotor in between. Let me have rotor conductors. Right? Let me have cross current here and let me have dot current here. This is rotor, shaft key. See here. Now, see here. What is the purpose of commutator? What is the purpose of commutator? Sometimes students say, sir, it is actually doing AC to DC, DC to AC and all stuff like that. It is doing rectification as well as it is doing inversion and all stuff. We know that from the standard books. But the main function of the commutator, I am going to explain you right now. Let us see what is that. See here, very important. I know you will say, sir, commutator is there in DC machine. Commutator is actually taught in DC machine, still we are teaching it here, no problem. Machine is a machine. We should never think that this is synchronous, this is induction, this is DC. Machines are machines. Basics for all the machines will remain the same. Always remember that. Now, see here. What will happen? This is cross, this is dot, which means current is entering in this direction, coming out like this, which means flux is in this direction. Which means flux is in this direction. This becomes north pole, this becomes south pole. Perfect? Yes. Focus here, focus here. See, this is going to become north pole, this is going to become south pole. What about my rotor MMF? Rotor MMF is like this, FR. Already we have discussed, because in the direction of flux only MMF is going to be there. Why? Because flux and MMF are directly proportional to each other. Now see here, what about stator MMF? Stator MMF will be like this, F stator. No problem. See here, rotor MMF is this way, stator MMF is this way. Now see, right? Now what about the torque? How the torque will be produced? See, if you see here, rotor MMF is this way, stator MMF is this way, and they are stationary with respect to each other right now. Right now, for this particular discussion, for this particular instant, if you see, rotor MMF is there, stator MMF is here, and they are displaced by some angle. We know that it is not compulsory that the angle should be 90 degrees. It can be any angle, everything will do, no problem. Now, the moment there is some angle, there is going to be torque. What about the torque? Let us discuss. This south will get attracted to this north. This north will get attracted to this south, which means torque will be in this direction. This is going to be the direction of torque, like this, right? Yes. So now, you please tell me, in a practical machine, will there be only two conductors? No, there will be many conductors here like this, right? And if I draw an axis here, if I see, then in order to have the rotor flux in that particular direction, all these have to be cross, right? And all these have to be dot. In the upper portion, all have to be dot, and in the lower portion, all have to be cross, because then and then only you will have current like this entering here, coming out, and there will be the rotor MMF. Now here comes the important point. We have discussed this previously also. We know these things already. We have learned this in this, stuff which we have discussed already in the previous sessions. Now, see here, very important point. For example, it is a motor, okay? Cross are the entering currents, dot are the outcoming currents, right? So, which means torque will be there in this direction, already discussed. Now I am holding the rotor of this machine. I am holding the rotor. I am holding it in order to, I am applying, which means I am trying to hold this motor. The moment I am trying to hold this rotor, what is going to happen? There will be a twisting moment in this direction, because torque is in this direction, right? There will be twisting moment. Now I am releasing it. I was holding it initially. Now I am releasing it. What will happen? Carefully observe. This conductor here will move here. Let us say this conductor is A and this conductor is B. Right? What will happen? This conductor will move from this position of A to the position of B. Now, if this conductor was having cross currents, then when this conductor goes here, it will also have cross. Again, if this conductor A had cross now, then after the rotation, this A will move in the place of B. The moment A is moving in the place of B, here the current is going to be cross. In the B position, current is going to be cross. And then again, cross will come here, and these dots will get shifted here. How? Because here also same thing will happen. The moment this rotor is going to rotate like this, this conductor will come here. This conductor will come here. Let us say this conductor is X, this conductor is Y. So here there was dot in X. Now what will happen when this conductor comes here in the place of Y? When X comes in place of Y, this conductor comes in place of Y, this dot will also be dot here. Which means when this will go on rotating, all these portions, all these here will simultaneously become dot. Means this conductor will come here with its dot. This will come here with its dot. This will come here with its dot. This will come here with its cross, dots. and at the end what we will have, in the upper portion we will have all the crosses, and in the downward portion we will have all the dots. Are you getting my point? Now, should this happen, sir? Should this happen? No, this should not happen. Why? Because we have already seen that second, that stator MMF and rotor MMF has to be stationary with respect to each other. Even if the rotor is rotating, see here, even if the rotor is rotating, MMF direction should not change. It should remain stationary with respect to stator MMF, and their angle has to be non-zero. Now, in order to have rotor MMF in the same direction of FR, all these lower conductors should have cross, and all these upper conductors should have dot, which means I need to design some arrangement. I need to have some arrangement which will, when this conductor moves here from A to B, this direction of current will get reversed. Are you getting my point? This direction of current was cross initially. Now, the moment this A reaches the position of B, what should happen? This cross should turn into dot. This incoming current should now become outgoing current, like this. Into the board current should come out of the board. Who will do that? That arrangement will be done by a commutator. Here will be commutators. See here will be the commutators. Because of these commutators only, what is going to happen? Whenever this conductor A will occupy the place of B, when A will occupy the place of B, its direction of the current will change from cross to dot. If this commutator is not there, for example, if this commutator is not there, what will happen? This A conductor will occupy the position of B conductor. A conductor will occupy the position of B conductor, but it will have cross only. Why? Because you are injecting cross into it. But because of the arrangement of commutator, this conductor, even if it is moving from A to B, the moment it is going to cross it, the moment this conductor A is going to cross the commutator, the cross direction of current means inward currents will change to outward current. How it is actually happening, that we will see in DC machines. But for time being, this is what happens because of a commutator, which means the first and foremost important work of the commutator, or the function of the commutator, is to maintain the stator MMF and the rotor MMF stationary with respect to each other, and it should be displaced by some angle. That condition is satisfied by commutator. Remember this name, commutator. We will be talking about this commutator in DC machine. Thank you.